Okay. Thank you to be here for the lecture of today. And of course, Happy New Year. Yeah, what we did until now, I presented basically in the context of the extended Kalman filter. I presented an example. Yeah, you remember the example was the estimation of the parameter in the context of a DC drive. Estimation of a parameter in the example which I presented implied an augmentation. Now we will repeat in this with another example. What is the meaning of augmentation? We generate a nonlinearity. Question which we try to answer today and next week. How many parameters can I estimate? How large can be this augmentation? This is the very important question. We will see this is connected with the observability of the system. Because if we lose the observability, assuming that I have the observability, if I don't have the observability, I cannot do anything. Because observability, roughly speaking, means invertibility. Means that measuring something, I can reconstruct something different. Practically, it means that the states are connected. But of course, it's intuitive to understand that given some measurements, if I augment, it could be that if the measurements, the number of measurements remain the same, I cannot invert the system. It could be that I lose something. I mean, if I have a few information, I cannot know everything about the system, just roughly speaking. This means how is the limit? I'm sure that I will not able to answer today this question because I have to reconsider the nonlinearity and the observability concept in the context of the nonlinearity. This we will answer next week. But with this example, we can try to apply the augmentation to another system and then to introduce this question, and in particular to do another example with MATLAB Simulink, which should I upload now? MATLAB Simulink? No, I can upload later. No? Look at this. This is a real project. We can see that this is some years ago we concluded that this project, and of course here in the lecture I have just an excerpt, just in a part of the project, the simplification of the project, because on the project worked many people. No, the project was at the University of Leipzig. Together with the research center. Look at here, desiccator system using radio frequency generation. I am presenting this system because how possible to say, I would like to show you a practical example, even though in a simplification, because Kalman filter really is applied almost everywhere. Next week, or during the next week, I will present also Kalman filter in a different context, in the context, for instance, of Lotka-Volterra equation, prey-predator. I don't know if you know, infected susceptible in the COVID, and so on. Here, just in a picture of the real system which we have, but let me go ahead a little bit quickly, just to understand that really it is applied, even though I already told you that I worked with the Kalman filter in the context of automotive with Volkswagen, in different contexts to estimate slip of the car, to estimate or to help the navigation, the cruise control, or auto parking system, and so on. Let me go ahead didactically, more in depth. I have what is desiccator. Desiccator, probably you know what is a desiccator. This is a system which is able to reduce at least the humidity in a wall or in an object. How is organized the desiccator? Basically, it's a capacitor. The object to be desiccated is inside this capacitor. And of course, we can see we have a warm electrode and a cold electrode. and the system is organized a little bit technically with this capacitor, let me say. We have two plates with two electrodes. Voltage between the two electrodes generates a current, very, let me say, must be controlled, this current. This means must be controlled this voltage. It's a current with relative high frequency. We can see here a little bit, very high at this frequency here, in this range. But the idea is anyway, I don't want to go in depth on technical aspect. The idea is to control the amplitude of the current. This means the amplitude of the voltage. Together, in general, also with the frequency. But I don't want to now to go in depth on the really technical aspect. We have nevertheless a matchbox system, which allows, I don't know if you are expert in electronics, to adapt the impedance of the generator with the impedance of the load. But forget if you know how to engineer. Basically, for us, very important, and to see in general how we can image the system, we have the electrical network, we have the radio frequency generator. Of course, the project, as I told you, we work, I don't remember how many people worked on this project, expert in electronics. I am not expert in electronics. I was, my task was the Kalman filter, the algorithm. We are here to think mathematically, act algorithmically. Also, concerning the matchbox, I know that we have to adapt the impedance of the RF generator with the impedance of the load, but just with the name, I'm not able to explain exactly. A little bit, yes, because basically I'm an electrical engineer. It's the question of the power transfer to adapt the impedance. But in this course, it's not important. But it's important, nevertheless, to know that exists this element here and must be modeled somehow. In our course, as a system theoretical experts, when we are working together with these electronical guys, we say that we have a system which is quite, I don't want to say complex, but consists of inductance and different things. And then they gave us an electrical scheme, also in a mathematical expression or description of this. Now, didactically here, I simplified this inductance model of the matchbox with an inductance L, because in this course, we can conceptually understand, in my opinion, better if I simplify. Of course, we can see that the system is a little bit more complex, but again, this is a project with involve many experts and many years in general. Basically, the system of the desiccator, the system altogether, can be, for us in this course, modeled in this form. For us, didactically, we have an LRC circuit, but which reflects or which models something like that. We can see here a little bit more practically what is the meaning of this and a possible structure of the desiccator. Using a desiccator for small object, for alimentary elements. I can distribute, for instance, tobacco here between these plates. We have many plates with state a series of capacitors. If you are not an electrical engineer, forget. But anyway, I can put some object inside. I feed the system. I generate, let me say, high temperature or controlled temperature, and I eliminate the humidity. Yeah? Just to give you a feel. The temperature is not in this model. We will see now. In fact, the model is just an electrical one. What we did, of course, in the project, we considered also the temperature as a state. But in this course, it is too complicated, because including the temperature, we have a physical nonlinearity. You can imagine that, because let me say, the thermodynamical model involves concept a little bit more complicated than this system here, which appears. I didn't describe C, R, and L, but we will see it's still linear. It's still linear. But in any case, it's not far away what we did at the beginning. I mean, we can calculate, please pay attention, calculate, not observe, the temperature using the voltage on the capacitor. But of course, it's not so precise with respect to the model which includes the temperature inside. But of course, the drawback that with the temperature, we have a physical nonlinear system. Let me show a little bit ahead what I intend. If you apply the Kirchhoff law, as we have seen in the electrical part of the model of the DC drive, believe me, I don't have much time now to go in depth how we can build these two equations or these expressions. But if you think about that, I can build a model considering the Kirchhoff law, the current balance here, this current here equals this current here plus this current here, and then I can build the equilibrium of the voltage. This voltage here equals this voltage here plus this voltage here. I don't know if you remember at school, but if you are not an electrical engineer, forget. We have a model. We will see in the next lecture different models in which you can understand very well that it doesn't matter where the model comes from when I have the model. I mean, if you are expecting Kalman filter, there is an electrical engineer that gives you the model. In another course, I presented that SIR is this COVID. I told you that I work a lot in COVID. The COVID model. I will show you next time. In which the equations is nonlinear equation, structurally nonlinear equation, physical nonlinear equation. But when we have the equation, it's not far away from this one. Of course, this is the linear case. The SIR is nonlinear, but we have the equations. Yeah, a linear system here, two states. It's quite similar to this to the equation of related to the DC drive. I mean, the DC drive, we have an electrical part and a mechanical part. Here is just electrical. But you remember the similarity is that we have a system with two states. We have two energies, electromagnetic energy because of the presence of this inductance. We have electrostatic energy because of the presence of this capacitance. We have two states, linear in both cases. Now, assuming that I would like to estimate not only one parameter, as we have seen in the DC drive, but we have to estimate two parameters, R and C, for instance, or if you want, R and L. And the question we will see next week, I would like to estimate now, as I told you, R and C, for instance, measuring U1 input, and you can choose U2 or I1. Question is, may I also allow me to estimate everything? Everything means also L? This is an interesting question. Without, please pay attention, increase the number of states which I'm measuring. So of course, look, measuring U2 as a state, it seems to be clear that I can reach some results. But of course, measuring also the current, it could be that I will be able to estimate something more because I have more information. Look, now the trick is, as we know many times, if I don't have any idea about the model of the R and C, I will consider the derivative of the R equals 0. I will consider the derivative of C equals 0 because I will introduce Gaussian variable. I mean, if I give you a structure of R, a model of R with respect to the time, I can introduce this information also in the Kalman filter. But if I don't have, we have seen that we have the possibility, nevertheless, to introduce just a Gaussian variable. I mean, without deterministic part. During the semester, I will give you some more idea about the model and so on. Again, I will hold the lecture until middle February in order to recover what we, because I would like to nevertheless give you more information about. I mean, we have 1 month at least a lecture. We can do. I hope that you can come also from Zoom the last period, even though you have examination. But I think the exams, the period starts middle February.
Starts in January.
In January. But anyway, I think you can come also from Zoom if you will not. I mean, this structure here we have seen last time, in which I will include 0, 0, 0 everywhere, because I don't have assumption, I don't have a model about R and C. I don't know if you remember. If you don't remember, I can come back to the augmentation of R. Let me see if I have here the file. I have it. No, this is the. I think I opened in the morning. Yeah. This is the simulation. I think it's here. This is always the trick. Yeah, exactly. The trick which we are using, which I explained, when we don't have any idea about the parameter which I want to estimate. I mean, I will consider the Gaussian variable. Remember, I introduced this at the beginning. Of course, if I have more than one variable to be estimated, I can eventually consider another row of 0, another column of 0. Question we will see next week, how many rows of 0 I can introduce. I can introduce so many row and column as long as the system remains observable. We will see really in detail with example, with calculations, and so on. Of course, it's a dangerous situation. It's a dangerous situation because I introduce in the model, in the deterministic model, in the matrix, something which I don't know, because the Gaussian variable is characterized by its distribution, but I don't have a structure. And the idea which I don't, the concept which I don't have structure is characterized mathematically of this 0. 0, 0 doesn't bring information, brings in the sense of Gaussian, but the risk does not bring connections. This means in order to avoid the not observability, if I have about the not observability, I will tell you a little bit more in depth in the next weeks, because if you remember, we have a test and a sufficient condition which say when the system is observable, what don't say when the system is not observable. This means, in any case, therefore I'm speaking about the risk. To obtain the observability, we can increase the measurements, the number of variable which I measurement. This means which I'm measuring, because I know I need more information. And or we try to eliminate some 0. What is the meaning? We need a model of R. R change with respect to the I don't know, the current in somehow. Of course, if I have a model of R with respect to the current, we will see in the different system. We have here not everywhere 0. Try to image. I will do some concrete example. I don't know if I share now because Yeah, I hope. Let me come back to the lecture of today. I think I don't need. Yeah, of course, we have here two parameters. Question is, let me try to estimate everything without checking the observability. Typically, we do, we check the observability. We will see next week for an easier system in order to, no, it's more or less the same. In order to consider another example, but in any case, similar to this one. Typically we check, but it's not necessary to check. Why that? Yeah, very often it's a little bit boring to check. Very often, intuitively, I can show you how we can see if it's observable or not. But in general, of course, scientifically, it should be better to check the observability because the test can say when is observable. We will see this means we have some conditions which must be respected that we can do something in order to obtain the observability. Again, this system here, as last time, is in a system which is, let me see if I have a better representation here, non-linear, because we have the product between R and C. R and C as the new or augmented states. We have one divided. Then we multiply by the states. Of course, it's non-linear. I don't know if you see it. U2, for instance, divided R of C, R of T, multiply C of T. Of course, we have a product. I divide it. I don't know if you remember the non-linearity. Okay, let me skip this because we know what is the meaning of this matrix. Yeah, if I do the discretization of the original system, I have this one. This without augmentation. This I told you many times about this. Let me go ahead now with the augmentation. Look, this is the vector which I am considering now as a state in which we have the two physical states, I1 and U2, two physical states, and two augmented states, artificial states. But states, the states are characterized here because I am considering their variation with respect to the time. They are included in the vector state because we are, let me say, observing, we are describing the variation of the states with respect to the time. This is the concept of the state, which reflects the energy. We reflect the energy because here we consider that the energy does not change just because we have a change in the current, I1 and change the current of I2, but because we are assuming that R and C changes. Even the energy change because of the presence of the changing R and C. This is the idea. But of course, in this context here, they are artificial, augmented, we say, the Kalman filter state. They are not physical. Physical. R is a physical parameter. But in the context of the Kalman filter, it is a representation. Isn't a representation. Please pay attention. Next week, we will see that we will test the observability on our representation, not on the physical system. Because what we know about the system, what we implemented in microcontroller, we will see today with the implementation. What we test, what we implement is our representation. And the representation must be effective. This means must be observable. Now, let me explain this. This is the discretization of this system here. About the discretization, I think I told a lot for a more easy example. using this structure here, using forward Euler approximation. You remember I told you we have many approximation or discretization, better to say. Forward Euler is what I present in this course. In my career, I work with different approximation, backward Euler, Runge-Kutta. Probably you heard about Runge-Kutta. The Kalman filter is different. This means the variations of the Kalman filter is also depending of the method which we are using. Look. How I can obtain this? Just roughly speaking. These two last equation, I don't know if you remember. This means R of k equal R of k minus 1. C of k equal C of k minus 1. This means constant. For each, if this is valid for each k, this means R of k equals constant, C of k equals constant. Exactly what I'm writing here. That the derivative equals 0. But we can see this expression here. Just if you apply this, you can directly apply everything in one step. I told you last time this, but here it's easy to see because we have R of k minus R of k minus 1 divided Ts equals 0. If I approximate the derivative in this form. Here I forgot, please pay attention, the dot. This is the derivative, x dot, please pay attention. We have seen in the other slide something better. I have to remember to put the correction. This is the derivative. And for C and R, it's clear that we have these two elements here. What about this expression here? But it's not far away because look, the derivative of the current using, for instance, again this is I1 of k minus I1 of k minus 1 divided Ts equal what? Everything which I have here, row multiplied column, calculated at time k minus 1, everything multiplied by Ts. Why that? Because we have a Ts in the denominator of the approximation of the derivative. And believe me, we will obtain this equation here. Because this part here, we can see 1 divided L multiply U2 plus 1 divided L multiply I1. We can see 1 minus 1 divided L multiply U2 plus 1 divided L multiply U1. What do I have in the right part? This I show you, I think, in detail once when I talk about the DC drive. You can do directly in this form here. This is the identity matrix, which justify here in the discretization the presence of 1 here. Once we multiply, we have 1 multiply k minus 1, which is also present here. Anyway, look at this form here. We can discuss together eventually if it's not clear. This representation here is in the Kalman filter. Why that? Because you remember the idea. X hat minus of k, this part here. And here is the function not of minus, but the a posteriori correction. We can see here. In some books, we have also here this hat. Should be better also here. I1 hat, but I didn't put here. Otherwise, it's very heavy also the notation. But in some books, we have this hat, and so on. Hat here, hat. But without minus, remember the difference. Because with minus here means a priori. Jacobian. This is the definition of the Jacobian. Let me calculate a couple of elements. Why this is 1? It's 1 because we have to calculate the derivative of I1 with respect to the derivative I1 of k with respect to the derivative 1 of k minus 1. You remember I explained this in the extended, the idea of the extended is to approximate with the Jacobian or better to say, is the Taylor approximation. The Taylor, I don't know if you remember this, the Taylor approximation of the a priori, for instance, in this case in which the nonlinearity is in the state, is the approximation of the a priori error covariance, let me say, prediction, using Taylor, as I told you. Of course, here it's a little bit complicated because we don't have just one variable, but we discussed we have many variables, means I have these matrices instead of just one derivative. But it's the matrix of the partial derivatives, if you want. Yeah, I think I didn't forget anything. At this moment, the nonlinearity is in the state. You remember I told you when I introduced in extended Kalman filter, it could be that you have a nonlinearity in the output. I will show you some examples. And in this case, of course, I have to approximate also the matrix H. I don't know if you remember, but let remain on this. Let remain on this. Why this is 1? Because it's the derivative of this line here. This is I1 of k. Better to say here, sometimes in some books, hat minus, hat minus, hat minus. But I didn't put, I don't want to really, to be heavy with the notation. Because in this context here, but it's not wrong. You can see that everything I called here with minus. But to be exactly precise, hat minus, hat minus, hat minus, and here, hat, 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 and so on. The derivative of this line with respect to I1 is 1. Clear. Why the derivative? Why this element is minus ts divided L? Because this element is the derivative of the same line with respect to U2. We can see here is minus ts divided L. Believe me, check at home the partial derivative, and you will see we can justify this expression here. There is in MATLAB the possibility to calculate automatically. Typically, if the system is complicated, this is not so easy. I mean, the derivative should be, we should be able to calculate the derivative, but the risk is that we make some mistakes. We have the possibility to calculate automatically, we have the command Jacobian. Look, help Jacobian. We have the command diff. MATLAB can help to avoid some mistakes. Here I did by hands. Why this 0, 0, 1, 0? This is easy, no? Because this is 0, this is 0, this is 1, this is 0. Why that? Because we have just the dependence with respect to R. No? The derivative with respect to I1 is 0. The derivative of this line here with respect to U2 is 0. The derivative of this line here with respect to C is again 0. We have just one element equal 1. We can apply. We can apply. Let me see if I forgot to say something. It could be, it's not the case. We can see, it could be that the Jacobian depends also to U1. I forgot here 1, the input. We will see in the future what is the meaning, but it's not a particular meaning. But if it depends, anyway, the input we know, because the input typically is the something which we put in an input. Is accessible, this element here. In our example, is this voltage here. Or the current, depends what we want to consider in input, but in our case, the voltage. Yeah, we can see here, U1. Not U, but U1. Also here, I have to correct a little bit the notation. Okay, let me show you in MATLAB. Let me see if I forgot to say something. The rest of the Kalman is the same. Here, H capitalized equal H not capitalized, because we don't have nonlinearity in the output. No? The output, what I'm measuring here, or the equation, here I didn't put the nonlinear I mean, do you remember y equals h not capitalized of the state? In our case is what we are measuring, for instance, U2. We can measure here, for instance, U2 as the state measured, or we can use I1. But please pay attention, in the output could be, I tell you about that, I will tell you, could be also a part of the model. This is, I didn't tell you until now, this is the meaning of this. But I can split, we will see an example, I can split the model in the state and in the output equation. This could be another possible variation of a Kalman filter. Output, let me see, model Kalman filter, let me see. Okay, let me look at MATLAB. So we see the implementation. But I have in mind tell you something, but I don't remember what now. Okay. Let me share. Okay, let me see. Let me see if I find now quickly the material. Ah, found it. Okay, no, this is not, where is now? Here. Okay, found it. Look, I will upload at the end of the lecture this file here, initial. Let me see if it's always active. I will do immediately. Yeah. Let me upload here MATLAB files. MATLAB means also Simulink. I share what I am doing, because otherwise I will forget. Okay. You will find initial with initial values. Let me do exactly. And then you will find to Simulink file, even though I have a time just to analyze one of both, I will consider the voltage measurement, but we can see that we have also the possibility to measure the current. No? We can see three files. One is the data file, then the version with the measured state, and then the version with the current state. Of course, if I measure both, the level of the observability increases. And of course, I can estimate better or more variables. And we will see this next week. We are in the case in which nonlinearity, at least in this model here, is not a physical nonlinearity. It's the nonlinearity which came from the augmentation. Because I augmented and have the product division and so on. We will see that if the nonlinearity came from the physical system directly, to observe the system, let me say, is easier because we didn't introduce the Gaussian variable. The Gaussian variable is something not structured. No? The derivative was zero. In this matrix possible representation, we have many zero. Zero is not so, we don't have connections. If you have a physical nonlinearity, this means we have connections, physical connection, no many zero in this possible matrix representation. Please pay attention. We are in the presence of a nonlinear system, and I am speaking about the matrix representation. This is not so quite orthodox because the matrices can be used in linear system, but I don't use the algebra of the matrices. I use just the representation, a possible representation, because I can do row multiplying column. I cannot use the algebra of the matrix because it's not the linear system. It's not, let me say, yeah, just let me, I don't want to go in depth on this, but we can understand. But intuitively, I would like to show these zero elements, which says that we don't have connections. Very often, I don't use in the project, we will see in the next matrices, because once understood the concept, the observability, we can proceed directly with the equations. Let me show you now this. Yeah, let me open. Yeah, looks like something like that with the real system, with parameters. This is the true, please pay attention. This is the true, our true. We can speak about true, yeah, because we put the values which we know sampled. Why this one? I told you a little bit. I didn't tell you about the Shannon theorem. I didn't tell you, but in any case, I told you that should be not so large, should be not so small. You remember, I will come back during this month a little bit. Run. Let me open now one of these two files. You can test at home. Current measure. I would like to show you the voltage measure because it's exactly what we did in the project. But I don't see. Ah, no, here. Yeah, you can see. Let me open. Let me show you. One second, I need time to upload. Okay, we are almost, let me share Simulink. Yeah, here is the system. Basically here inside, basically here inside, I realized the linear system. Please pay attention. An interesting discount here. The system is linear in its nature, but in our representation becomes nonlinear because we want to estimate C and R. We want to estimate C and R. Of course, try to do at home if you want to change here as a possible exercise. C and R over time. The Kalman filter will estimate this. I told you also in another example, even though I never presented this, but it's not so difficult. If you multiply here by R and you invent a variation of R over time. Anyway, it's constant. Here everything is constant, but we don't know the values. But believe me, if I change here over time, Kalman filter will estimate. Now, the scheme is always the same. No? We have an input delayed because UK minus 1 or U1K minus 1, the input which we have. Radio frequency, a sinus in input. We measure U2, the second variable. And here inside we have the Kalman filter. Let me show you what we have. I copied here inside exactly what I told you in the lecture, but we don't have, it's in a technical aspect, we don't have an interpreted file. Do you remember? Interpret. Now we have an embedded. I show you what I intend. Basically, it's quite similar, a little bit more complicated didactically, but for the implementation is we can direct flash these files in the microcontroller. What I intend is this one. Here we have the real system. Our microcontroller is here. This part here can be flashed directly in the microcontroller. Of course, this is not there because we simulate an error in the measurements of the voltage. Of course, the error must be Gaussian. We know everything about that. Also this one. No, we simulate an error in the measure of the input. It could be noise. What we are doing in this course, the noise must be Gaussian, white, and so on. This is the hypothesis. If it's not, we have a different Kalman filter, which I don't have time to tell you. Now, we can pass these two values, also everything which is constant here, with parameter here. I didn't tell you it. I don't want to be heavy with the notation, but we can introduce here comma, more variables, or the more parameters. Here, X is not a parameter, it's a state. Yeah, state in the sense, one is in a state, one is in an input, if I remember well. Yeah. One is in an input, one is in a state, the measured state. You can see. But the new thing, the technical new thing in this embedded file, instead of interpreted, I have a two persistent variables that is the variables which I need for the next step, which I define inside as the persistent means remain. Because I will not update externally, I will not pass the new value externally. Do you remember the max, it's complicated, a little bit complicated, but conceptually easy to understand, but everything inside. But of course, you remember in the interpreted, we have initial value, 1 divided z, and inside the initial value, I can put, inside the 1 divided z, I can put the initial value. Here, I have to put the initial value inside the embedded. Look, if empty, my variable x alt, one is empty at the beginning, put three initial values, excuse me, one for the current state, the physical state, one for U2, the second physical state, one for R, augmented state, one for C. We can see that I make a big mistake at the beginning for the initial value of R. The real value is R equal 1 is 5 times, extremely high. Here I put also in a big value, big, because here was 3, 10 up to minus 3, C, almost twice. Could happen that the extended Kalman filter does not work, because the extended Kalman filter is a convexification, because I'm considering a linear system. But the original system is not, the original optimization problem is not convex. No guarantees. In this case, absolutely no guarantee, because they're really far away. It could be that you have not a convex region. I do the same for the a posteriori covariance matrix. Remember, I told you a lot about that. Please pay attention. With all 0, I am waiting for a very lazy Kalman filter, because I am saying to the Kalman filter, as an a priori knowledge, please be quiet, because we are already at the goal, because no error at the beginning. Of course, this is an assumption. What I am doing is an interesting project in medical system, in which we estimate some hormones as an insulin detection or identification in diabetics patients, to calculate using PSO, particle swarm optimization method, this element here at the beginning, and also additively Q matrix and R. I don't have time here. It's a PhD program. But of course, the problem of the Kalman filter is, I told you, these two elements, the matrices, is an element because we measure just one state, and the initial variables. But we have a method with neural networks, with particle swarm optimization method, probably you know, in order to check at the beginning and to update at each step how we can get knowledge about this. But it's really this extremely advanced. We do that in master thesis. We can do also here, no? But not in the lecture, because it's, the rest we know. This is the variable which I'm measuring. The input is the state which I measure. Then I have current state, which I rename. I rename. Very interesting. This x alt, p alt, they are internal variable now. Here is what we estimate, and line and this line, what we estimate. This is the voltage, what we measure. We measure U2, the second variable. Ah, wrong. The second variable is the voltage, but a comment. And then I copied the a priori approximation. I copied the Jacobian from the calculations. The rest doesn't change. Let me show the simulations quickly, then we conclude introducing the lecture of next week very quickly. What is here the problem? Basically, we can see here at the end, compare R, compare C. We are waiting something very lazy, because P0, the initial error, is 0. And we are really far away from the truth. This means Kalman filter say, before Kalman filter understand that we have to do something, we need time, because at the beginning they don't have high K to correct, because I'm saying a priori, be quiet. We have already the right part. Look, I am concluding. Let me look at R. This is the critical one in this case, because of course, what we are measuring, we will see we can estimate quite good, because we are close to the information. What we are measuring is not the truth, please pay attention. But it is something which you measure. This means the information is there. Let me show you this. Yeah, we can see how lazy it is. Try to do at home to put something larger in in the value of the matrix P, the corresponding to the R and corresponding to the C. We can see, oh, this is the lazy. You can improve here. The same for C, no? And also similar mistakes we can see in at least in the current, because the current we didn't measure. Try to at home to vary this in the model. Starting from this value to have a sinus, cosinus, or increasing. We will see the Kalman filter full of this. We discussed a little bit this. Look, I think a similar error could be in the current. Yeah, in fact, you can see. Before the current will be estimated correctly, he needs the time to have a correct value of C and R. Correct value of C and R. Makes sense, because the system is connected. Everything is connected. What we are measuring could be, but not necessarily, it's better, almost perfect, I think. Let me show you. It is. Because we are measuring here the information, what we estimated is close to the information. What we can increase the performance, try to do at home. For instance, writing here instead of 0, I don't know, 10. How much I'd have to write? This is a big problem. PSO neural networks can help us at the beginning to run what I'm doing now. Now should be, we can see here. Now this is the results for one of them. This is the resistance, yeah? We get the results at 10 seconds. Let me see if we are able now to get better results. Better means a little bit earlier with less amplitude. It seems. Yeah. Yeah, interesting. Try to do at home. What we do next week, we are concluding. How many parameters can I estimate? I don't know if you remember one of the lecture at the beginning of the semester. We will check together. I'm reading. The observability, let me share. One minute, I'm concluding. Next week with concrete example, because otherwise it's too theoretical, we will see how many parameters I can estimate. We will see, here's the problem, which conditions I need to estimate more parameter. I will tell you a little bit very shortly about the concept again of observability in nonlinear case. And then we will do some example applying this method. The method is fine, this condition here is observable if, with relatively easy example, but extremely clear. for the lecture, and to find conditions which we have the sufficient elements to say is observable. But of course, it's a sufficient condition. This means if it's not satisfied, we cannot say anything. Could work, could not work. But in any case, it's quite constructive, because sometimes we have with this rank, with the results, because sometimes we have here, and we will see next week a little bit more in detail, conditions, when the rank is full or not. Then we can measure another variables, we can consider which one can be measured, and so on. I will tell you next week this in the context of the augmentation. Then we will go ahead with the physical nonlinearity, and we will conclude with variations of a Kalman filter, cascaded Kalman filter representing output. Remember the Jacobian output, I didn't tell you until now. Now the nonlinearity is in the state. Of course, this is the most difficult case in which we introduce as a state something which I don't know. Oh, I know in the context of Q. You remember Q could, I didn't tell you today about Q, but last time I told you a lot. Q large, Q small. If I have knowledge about the variable, of course, Q is the variance or the covariance elements is smaller. Here, typically, if I don't know anything. Okay, let me close the lecture. Thank you. Excuse me again for today, for my being late today.